All right, thank you. Printing the future in 3D. Hello everyone, my name is Sam Buls, and I'm a research engineer in additive manufacturing, also called 3D printing. Within 3 years now, I'm also doing a PhD dedicated only to additive manufacturing. When people ask to me, hey Sam, what's actually a PhD in additive manufacturing? And then I try to explain actually what I do, and that's sometimes quite hard, and I get the most rare projections of myself. Mostly, they say you're a geeky one or you're a sleepy one. Actually, what I try to say to them is, a research engineer in additive manufacturing, what I do is I try to build the next generation of 3D printers. I try to develop and I try to implement the new technologies in those 3D printers and start to validate the new technologies. Meaning I'm active in several types of domain of machine construction. Domains like mechatronics, advanced control theory, real-time programming, laser optics, all those kind of things. My university, where I do my PhD, is located in Leuven. Leuven, Flanders, Belgium. Leuven and Flanders is actually very competent in additive manufacturing. In Leuven only, we have 2 global companies. One of them is Materialise, famous for its software, Magix, and specialized in production on polymers. On the other hand, we have a company called Layerwise that specifically focused themselves on production on metals. The 2 companies are also spin-off companies of the University of Leuven. And also in our university there's FabLab. FabLab is actually a lab where people can come to and make and design things that they want to do for free. There are some 3D printers and you can use the 3D printers for free. Actually, a couple of years ago, together with some of the DevOps members, we created the voting system outside the conference room in FabLab. In Flanders also, there's another company, Melot, that's also specialized in production on metal parts. Now, those are only the companies active in additive manufacturing in Flanders. We have several universities also working in additive manufacturing, and we have the other research centers like Series FMTC, which stands for Flanders Mechatronic Techniques Center, Flanders Drive as well, Vito, all those kind of research centers. So yes, Flanders is very competent in 3D printing. The professor which I work for, my promoter, last week he got an award, a famous award, which clearly say that it's competent in additive manufacturing. Also, this award was given to scientists like Albert Einstein and Marie Curie. So yes, Flanders is very competent. If you ask to me, when did 3D printing start? Well, that's a difficult question. We started 20 years ago, but actually 3D printing started much before 20 years ago. To give you an exact date on that, we should go have a look in literature and see when articles starting to pop up describing additive manufacturing. Luckily, there's a service from Google called Ngram, in which you just can enter certain words, and it looks through all the books starting from 1800 until 2000, and it's just collecting words that describes in the books. And what we can see from this graph is that additive manufacturing started around the late 40s, and that now today the term rapid prototyping is one of the most popular terms. This is also something that the government sees. Additive manufacturing is gaining huge value in the industry, and the government tries to invest huge amount of money in additive manufacturing. To give you a general idea, this is a list of some countries and continents, and also the amount of money that are going to invest during the couple of years in additive manufacturing. What you see from this list is that China and also Europe invest lots of money in additive manufacturing. So yes, there's going to be a big future for 3D printing. The whole story about 3D printing in the industrial point of view starts with 3 main players. One of them is the industry, the machine constructors, and also the research centers. It goes actually like this. For example, if the industry comes with a problem, let's say they have a big turbine that costs a lot of money. It's huge. It's one of a unique piece, and it's broken. The problem is if you have such a large turbine and you need to have parts for it or repair it, it's extremely expensive. You cannot just buy a new turbine for an energy company because it's too big and you have to wait several months to get your parts. Even the molds for making the blades on a turbine, if you have an old machine, they're probably gone and you cannot make new blades for it. So maybe we can make the blades with 3D or additive manufacturing. The first thing you need to ask to a machine constructor, is it possible to have a machine that can handle such large parts? That's the first question. Other questions goes to the research center. For example, is it possible, if you have a breakdown of such a turbine, to add material to the axle where the bearings used to be, and to gain a certain hardness so the bearings will work properly? Is it possible, if we have some broken blades, to print the blades instead of going to the conventional way of making it by a mold? Is it possible to print the blades out of Inconel? It's a type of steel that can handle extremely high temperature. Can we print in monocrystalline? It reduces the creep, and it's also very good in turbines. And maybe it's also possible to directly print a ceramic coating on top of the blades. That's questions that we get. Other questions like, is it possible to print directly internal cooling channels in the blades for an optimal cooling? Those questions we get the research center. When you're going to make a part, you can either choose two ways on doing it. The first way is a subtractive manufacturing. Actually, you buy a bulk material and you use technologies like grinding, milling, turning to get to your end product. That's cost intensive and you also lose lots of material. Another way on making a part is by additive manufacturing or 3D printing. And also in additive manufacturing, you have several kinds of technologies available for making a part in a 3D printing way. For example, fused deposition modeling, long for FDM. This is actually an extrusion-based technology. You have an extrusion head, you put in material, you heat it up, and you extrude your material to a very small nozzle, and then you can lay down your first track of your material. You can move the nozzle, and you can build in a 3D way your part. This is going to be a topic, I think, tomorrow also in a talk. I'm going to focus this talk on selective laser melting and selective laser sintering. In comparison to the extrusion-based technology, SLS and SLM is actually a powder bed technology. You start with your material in a powder form. Like if you have aluminum, you can also make powder from aluminum. And then you can selectively melt certain parts of the aluminum to form a solid. In that way, you can create 3D models. Those are several technologies available today. Now let's have a look at some materials that's available today. We can print metals, polymers, and ceramics in powder form. Now if you have a container with metals inside a powder form and you have a container also with ceramics in powder form, it is possible to add a little bit of the ceramic material in the container with your metal parts, shake the powder, and then you have a new material called ceramides, ceramic and metals. You can also do the other way around. You can add a little bit of metal to your ceramic powder, shake it, and you have a complete new material called ceramides. It's also possible to not print, but to dope some living cells into a 3D printed object. And then hopefully the cells will grow and you will get what you want. This is an example of the materials that we use mostly, copper, aluminum, and the third one is actually a special one. It's steel and a polymer. You have normal steel, you have steel in combination with copper, and you have also wolfram carbide. Some of the materials are quite durable to print, but there are some other metals that are quite hard to manufacture. Like the copper, for instance. Copper has the very high thermal conductivity, which means if you inject heat the heat will dissipate away, and it's very hard to process materials in copper. That's still research now today. Now let's see which industries are questioning for 3D printed objects. And that's actually started from the aerospace until the food industry. It is possible to have a nozzle, put some tomato sauce in it, and then try to print with your tomato sauce in your pizza kind of figure. That's possible. This is a schematic. It's commonly used to describe how selective laser melting and selective laser sintering is done. Everything starts in the build platform. That's the space in your 3D printer where the part is being built. On the other side, you have also a feed container containing your material in a powder form. And you have a scraper. The scraper can move from left to right and from right to left. The scraper can deposit a very thin layer of your powder material on side of the base platform. And by thin, I mean sizes of 30 to 50 micrometers. So yes, very thin. Once your layer has been deposited, that's the first step. The second step, that's where the laser comes in. You also have a laser, and the laser can shine on your powder bed. There where the laser shines, you will create heat, and you will melt some of the particles together. They will cool down, and you have a solid in your powder bed. The third step, the build platform will go down one layer, and the scraper can deposit a new layer on top of the old one, and then the whole process repeats itself. In that way, you can build a part layer by layer, and after several hundreds of layers, you will have a build cylinder which still contains loose powder, but in the loose powder, you will have your built part. That's how you build parts in a selective laser melting or sintering printer. Now, selective laser melting is very easy. You just heat something up until it melts. Sintering is another story. If you're going to use sintering, then you're going to heat up the material, but not until it melts. Just below melting temperature, then you have the sintering temperature. And when you're going to sinter, you will diffuse some of the powder particles together where they meet, and also form a solid inside of your powder. The only problem is that you will achieve not a high density. That's something in some applications that you don't want. This technology is used mainly in materials that have a high melting point, so you can just lower it by only going to the sintering temperature. Commonly used technique as well. Okay, so now let's make a part. The first thing you need to do is you need to draw a CAD model on your computer. In here, it's just a scaffold. The second thing you need to do is you have to use some software to slice your 3D model into certain slices. Slices that have a thickness of the thickness that you're going to use in your machine, 30 to 50 micrometers. And all those slices need to be filled with a certain scan pattern, the pattern that the laser will follow. Okay, you have your file with several layers and the scan pattern, and that file you will just copy to your machine, and then the machine will take the first layer, scan the scan pattern, it will deposit a new layer, scan the second layer, and so layer by layer you can build your part. The next movie is a movie with a camera inside an SLM machine. So in here you will see 4 parts being built. There are the identical parts just for process production. And you will also see afterwards the recoating. And so the whole process repeats itself. All right. This is the first metal part that I have built at KU Leuven. You can see that the quality is quite bad because you can really see the layer thickness. This was about 500 micrometers layer thickness. Now we can go up to 30 micrometers layer thickness, meaning we get better quality products. This is a photo of some of our demo parts at KU Leuven. Now I want to point out your attention to the third part. That's actually a ring with support material. If you are going to build a part in loose powder without any solid material touching it, you will have a bad quality part. The heat you inject will stay trapped in the powder and you will get dross formation and the whole piece is just bad. So what we do is we build support material starting from the base plate up and then really attached to your part that you're going to build. In that way you have a good thermal conductivity and the part is being held together. Now let's have a look at some applications in which additive manufacturing could be used, some industrial applications. This is a hinge from an Airbus A320. On the left side you can see the conventional part and on the right side you can see the additive manufactured part. Now this part has been topology optimized, meaning we can take out some of the material, reducing its weight, but actually with a minimum impact on its total strength. So you still have a good product, but the weight has dropped dramatically. That's a huge advantage in additive manufacturing. We can really create and design parts that are very strong and very light. And actually some parts that cannot be made by conventional machining. You can make a bowl, hollow bowl, and that you cannot, or it's hard to make in a conventional way. Other applications in the aerospace technology is this bracket. I mentioned earlier that it's possible to combine some of the powder material. Well, here we combine steel and a polymer, and we can also create new materials with this material. It's functional and it's very light, and also it has some more stiffness than a normal polymer part. So that's also a huge advantage. Another application is in the plastic industry. This is a mold for an emergency button, the red mushrooms where you can push on. A normal injection mold is a mold that you can place into a machine. You heat the mold up, you inject plastic surrounding it, you cool down the mold, and then you can just subtract your plastic part. The problem is with the conventional way, if you heat up your mold and you cool it down, the cooling down is actually done by circulation of cooling fluid in cooling channels. Now the cooling channels are straight through the mold, meaning you will have an ununiform temperature distribution in your mold. This will induce thermal cracks in your plastic material and you might damage the plastic part you're going to make. That's something that you don't want. What we have done here is we redesigned the plastic mold with internal optimized cooling channels. This cannot be done by a conventional way. You can drill a hole, but you cannot drill a curved hole. And here you can clearly see the curved inner cooling channels, meaning we have now a conformal cooling of the mold, and our plastic parts that are made by this mold have a higher quality. Those are typically applications now today in additive manufacturing, the internal cooling channels. This is quite relatively a small piece, but it's also possible to build bigger metal parts. This one is also an example of a turbine, just to indicate that it's also possible to build very big parts as well. Big, I mean between 10 and 20, 30 centimeters. There are machines that can build large parts as well. In Materialize, they build their own machines, and they're like 5 meters long, 2 meters down in the basement, where they can build a whole dashboard from a car out of one piece. So that's also possible. Another huge industry that benefits from additive manufacturing is the dental industry. This is an implant for teeth, and it's customized to fit on a human body. So it adapts very well, and it's very easy to implant it in a human body. This one is made out of titanium alloy. Now, we can also make our own material in a powder form. And last research was done on nitinol. Nitinol is a special kind of metal which has a shape memory effect. I have an example of nitinol here that has been 3D printed. And hopefully that the camera can see this thing. So here you have just a nitinol spring. You can deform the spring. Try to deform the spring. Okay, now I've deformed it, and by just applying some heat to it, you will see that it tries to go back into the shape it originally was. Do it once more. Deform it. And then hopefully it goes back into shape. This is nitinol. We used nitinol and made it in a powder form. And then we tried to build parts with it for the dental industry, which means if you could print a bracelet out of nitinol and you put it in your mouth, it will constantly apply a pressure on your teeth, meaning that you don't need to go to the dentist and you don't need to adjust the implant. That's something typically also done today with nitinol parts. It is also possible, and that's something for the ladies, to print jewelry. This is actually a picture from iMaterialize. So yes, we are able to print gold, and we're also able to make it very shiny. You can buy this on iMaterialize for, I think, 30 or 40 euros, so it's very cheap as well. iMaterialize is a service from Materialize in which you just can send your 3D CAD model, and the next day you will receive your part being built. So that's also very interesting. Another industry is the biomechanical industry. This is a scaffold. A scaffold is an object designed with very small pores into it, where cells can be doped into it, and hopefully the cells will then grow and you end up with a scaffold with lots of cells in it. An example of the scaffold is actually a cross-section of your bone inside of your arm. It is possible, if you have a fracture in your arm, to take a CT picture of it, reconstruct it, and make an implant out of scaffold design, and then try to dope some cells in it, and you will see that the cells will start to grow. This is also active research in KU Leuven. Now, what we've seen is that cells, they tend to grow faster, or bone cells, they tend to grow faster in a structure that looks like bone. So what we try to do is, we tried building some special scaffolds that mimics the structure of bone. It is possible now to dope in some bone cells, and they will grow inside of this scaffold. If you go have a look at some deeper inner pictures, on the left you will see a normal picture of optimized scaffold. If you go in and have a little zoom into the scaffold itself, you will see that the surface quality is very bad. And cells don't like it when you have a very bad surface quality. So what we do is, we then etch it to get a better surface quality, and that's the right picture. And now our scaffold is done for in vitro. So what we do is, we take some cells, we dope it into the scaffold, and then we place it in an incubator, wait for it, and then take it out, and you will see that there are cells growing inside of the scaffold. If you take a scaffold out of the incubator, put some fluorescent on it, then you get these kind of pictures. All the green thingies are living cells inside of the scaffold. So yes, we can make some special things out of this kind of technology. Research also has been done, not by us, but you will find on the internet this article, with a human ear inside of the back of a mouse. That's quite special. What they actually have done here is, they made a scaffold in the shape of a human ear. They doped cells into the scaffold, implanted the scaffold into the back of a mouse, wait 3 months, and then you have a full human ear inside of a mouse that you can later then attach maybe to a person, if it's biocompatible. All of the previous scaffolds were titanium-based. It is possible to create scaffolds on a biodegradable material, meaning that the scaffold will eventually go away inside of your body. So you will end up only with your own cells instead of an implant. That's quite interesting. Now, law prohibits us on doing research on animals, so we are not going to do those kinds of tests. What I did was, for the next slide, I would like you to introduce you to the Stanford bunny. Maybe you know him. It's a very famous bunny. It's actually a bunny that's used for GPU tests, and it's actually an STL for rendering proposals on GPUs. What I've done is I've took this bunny and I made a scaffold-like version of it. And this is the end result. I made several of those, and they seems to be quite popular in Leuven because I've made 10 and 9 of them got stolen. And I actually found one of them on YouTube for another research that was not mine, so it was very strange. This is all titanium and metals, but we could also use polymers instead of metals by using selective laser sintering. This is an example of the pieces that we make. It's just chess parts made out of polymer. But you could also make real functional parts out of polymers, like these, for example. These were printed in one piece, and they are quite functional as well. Now, if you ask to me, can we make anything without any problem, then I can say, really, no. We need technology, we need machines, we need material, we need parameters, and definitely we need research on how to make a good quality part, because we can build parts today, but the quality is sometimes not the quality that we want. And it's very hard to convince an aerospace industry. We can make parts that look good, but maybe they are bad. They are not going to accept that. And what we see now today is that industry asks us to build the same part several times. They do some destructive tests on 3 of the 4 parts, and if they are good, then it's okay to say, okay, that part, the other part, will be good, and they are going to use it in industry. Parts that are failed, or that are failing, is quite common today in additive manufacturing. That's why we also do some research on that. This is an image of a jaw with a huge crack inside of it. Now, the awkward thing is that the crack appears 3 weeks after it was being built. We built it, put it in a demo closet, and then after some while, 3 weeks, there was a huge crack in it. Well, that's actually due to thermal stresses. If you heat up a part by a laser very fast, it will get hot, it will melt, it will expand. And after a fraction of a time, you will cool it down, and it will contract once more. So you get expansion and contraction, meaning you will induce thermal stresses inside of your part. If you don't do this, if you don't get it under control and you don't take it into account, you will end up with this kind of failure. You do not want that this happened when it's also being implanted in a human body. That would be very bad. That's recent research also at the KU Leuven. What we do to fix this is we use preheating. We start by the powder material, heating it up until higher temperature, and then start the process. So the thermal shock is less, resulting in less cracks or even no cracks at the end. You can see at the left, we built a cube with no preheating, and it did not work because we got cracks everywhere. And then when we increased the preheating temperature until 200 degrees, we could eventually make a good part. This is actually high steel, M2 tool steel. Those are all industrial applications. It is also possible to have non-industrial applications, like the one you see on the media and also on YouTube. This is one of them, the 3D doodler. The 3D doodler is actually a Kickstart project, and you can clearly see that they got enough of it they are asked for. It's actually a small pen, which is also extrusion-based, where you can print with your pen in the air. But with further ado, I will just give you the trailer of the 3D doodler.
What if you could draw things exactly as you imagine them? What if you could lift your pen off the paper and create real objects? The 3Doodler is the world's first and only 3D drawing pen. It's been designed to be compact and easy to use. No software, no computers. You just plug it in and can start drawing anything within minutes. The beauty of 3Doodler is how simple it is. Everyone knows how to use a pen, so we designed a 3D printing pen. If you can scribble, trace, or wave a finger in the air, you can use a 3-doodler to create simple or complex objects. And we're making 3D creation accessible to everyone. A 3-doodler is the most affordable way to 3D print.
That's so easy. So if you don't know what to buy for your children this Christmas, this might be a good Christmas gift. Now this is the more home version, but there's also an industrial version of this product as well, not by 3Doodler, but by an industrial company. And here it is. That was the industrial version of the 3Doodler. 3D printing is also of an interest in artists. Artists use 3D printing technology to expose some of their creation. One of those artists is an artist called Marcus. He's a German, and he has made a 3D printer that operates fully on solar power. He uses sand as his building material, and he also uses the sun to melt the sand. I will briefly show also his movie. Very high tech. All right. Now, the parts that I've been showing today are quite big parts. It is also possible to build very, very small parts as well. This is an article that I wrote 2 years ago describing the 2-photon additive manufacturing technology. This technology allows us to print extremely fine parts as well. You can see there's a church on the bottom. The church has some features that are sub-micrometer accuracy. So yes, we can print very small details as well. This is not new. Also, IBM used some technology to print very thin structures. In the late 80s, they published pictures where they claim that they are able to print a single atom at a time. Now, they don't use this technology for additive manufacturing of building parts, but they use this technology for storage. So they can print a single atom that can be a bit in a byte, meaning that they can really pack the density of your hard drive. And it was until April 2013 that they published a movie about what you can do with it. The movie is called The Boy and His Atom. It's actually the smallest movie that's ever been made. All right. This was a movie that the smallest thing that I found to actually print or represent as an additive manufacturing way. The
Could the atom be rewritten?
Excuse me?
How often could the atom be rewritten?
That I have to look up. I don't know by heart. I didn't specialize in that technology as much as in SLM or SLS. That's the smallest thing that can be printed. The biggest thing that I found that can be printed was actually this. And by that, I thank you for your attention. If there are any questions, I would like them to answer to you. Yes?
Does the cracking problem which you demonstrated with the jaw also occur in polymer?
Cracking in polymer. There are several technologies which you can use to produce polymer parts, like SLS is one of them. You also have what they call SLA, stereolithography, and that's actually today also common use in making polymer parts. And what we see is that we also experience some cracking in polymer parts, yes.
Does the same solution also help?
No, you need different techniques. Preheating of polymers is possible. They do it in selective laser sintering, but in selective laser stereolithography, SLA, they don't use preheating. No more questions? All right, then I would like to thank you all.